Okay, thank you very much. Thank you for the introduction. So what I would like to talk to you today is about a few feed-forward methods we have been developing in Oxford and Meta for the reconstruction of 3D objects and also digital twins. So, the way I want to do this is by designing neural networks to solve the problem. So this is ideally going towards building a foundation for 3D computer vision, and also a foundation of vision in general, which is based on 3D, all right? And to do that, what we need to do is to have networks that solve the problem. So what do I mean by that? So there's a neural network, and you have a bunch of images as input, and what you want to be able to do is to say that this network has developed a three-dimensional interpretation of the data. And to show that, what we want to do is to extract from the network some 3D quantities, some 3D reconstruction, all right? So what we're talking about here for now is how to do 3D reconstruction using a neural network. Now, if you look at the traditional reconstruction paradigms and the way you typically do it in the past, say, 20 years or 40 years of computer vision, you would start with a bunch of images. The first thing you would do is you establish pairwise correspondences. So this is the white box here. And these white boxes, what they do is they look at two images at a time, and then using either something handcrafted like SIFT or maybe something learned, like superglue, they would establish correspondences between views. And then on top of that, there is some box that uses visual geometry and optimizes over these correspondences to try to come up with a 3D reconstruction or interpretation of the data, right? So there is the white stuff, which is feed-forward and learned, and then there is the yellow stuff here, which is optimization, iterated, all right? And so it looks something like this, all right? And this is fine, but it's not really great if you think about a 3D foundation or computer vision, because we don't really want the yellow stuff in the way. So you just want to operate with a network, and then maybe this network is very easy to integrate in a large language model later, and then you get 3D capabilities together with your next ChatGPT. So to do that, you need to get rid of yellow stuff. Now, more recently, we have seen tons of progress in feed-forward methods or neural network-based methods for 3D reconstruction. So you can now do not just point correspondences, but you can also do depth, camera motion, etc. Or more recently with Duster, I guess, we can also estimate point maps, which is a very, very useful representation. We're going to see more of that later. That really encodes a lot of useful information for 3D. But at the end of the day, what you get is still some pairwise approach. So you get image pairs, you run something, say, Duster, and then you get some pairwise information extracted from those pairs. And on top of that, you still need to do some optimization to fuse everything together into a single 3D interpretation. So we're not quite there yet. Okay, so we still want to get rid of that yellow stuff. So what we're going to do now is geometry in one go. Bunch of images input, big transformer in the middle, the 3D quantities you want at the end. So you're going to get point maps, depth maps, correspondences, well, in fact, features for the correspondences, as well as cameras. So everything which is needed to say you have reconstructed the scene in 3D is going to be there at the output of this network. We don't know what's happening inside. Inside is still implicit. There is no explicit 3D inside, but there will be explicit 3D at the output, and that's very important. So this model is called VGGT, and is a collaboration between Oxford and Meta. And so here we take a bunch of images as inputs. The first thing we do is we tokenize them by using something like Dino, nothing special there. Then we add to these tokens which are specific for each frame, the red tokens there. These are supposed to encode cameras. We put this into a big transformer, which has a little bit of structure, doesn't really matter, and I'm not going to discuss this in more detail now. You can refer to the poster and the oral if you want to know more about that. There's just a big transformer, essentially, and out of that you're going to get process tokens, which are the touch level tokens, the image level tokens, as well as these red tokens which encode the image level information as opposed to pixel level information. Then you get decoder heads, one for the camera tokens, another one for the image level tokens, the pixel level tokens. And out of those, you get the cameras, and then you get quantities like depth maps, point maps, and tracks, all right, or features that are good for tracking. Okay, that's the model. We just train it well, and we get good results out of it. So these are some examples. So you have 32 views as input. Put this into the model, and half a second, you get this as output. There's no post-optimization here. It's just feed-forward through a transformer, okay? The model is flexible. You can put in 64 views. It's going to work all the same. And you're going to get in about 1.5 seconds of reconstruction like this. If you wait a bit, you're going to see that you can also do 120 views. In fact, the model can go up to 300 views, although it's only trained to take up to 24, but because it's a transformer, it does generalize very well to longer sequences. So you can get this out. And if you really want to press the model, you can also reduce the number of views, and you can get the reconstruction from 2 views only, even non-overlapping views. This was already shown by Duster and Master, so it's not that new, but this really shows the power of doing 3D reconstruction through learning. So you get the ability of hallucinating also cameras to make them plausible based on your inputs. In fact, you can push the model even further, and you can get it to perform single view reconstruction as well. So this is our example of depth estimation, essentially results from single views that you can get in a fraction of a second. And it works quite well, indeed. Now, the important message here is that this is one of the first models that is actually competitive with methods that use bundle adjustment for 3D reconstruction, even though it does not use necessarily optimization. And this is really the key here. So here we see on the slide our reconstruction result of cameras on a real estate 10K, just a benchmark. On the left, you see methods that use bundle adjustment. Next set of methods are feed-forward methods that do not use bundle adjustment, and they are a little bit worse or on par. Now, VGGT is actually better without optimization, all right? And if you can really want to boost the performance, you can do so by running optimization on top. This is going to give you more percentage points in this benchmark and other benchmarks as well. But the point here is that even without doing that, you can still get excellent performance, which means a feed-forward model now can, at least in a large majority of cases, give you a 3D conceptualization or reconstruction to a level which is comparable with what in the previous years would actually require optimization instead. Now the model, because this feed-forward is also fast, so you see it that compared to previous method use bundle adjustment or that feed-forward, VGGT is as fast as faster, okay, which is a fast method, obviously, as the name suggests. So it's good when you are this fast. And if you add bundle adjustment, it's going to be slower, obviously, but not as slow as it was used to be for prior work, simply because of the fact that we land already in a very good solution that requires very few iteration of bundle adjustment to converge. But really, the point is that you can use it without bundle adjustment. This is simple. If you want to give it to your friend that does understand nothing about 3D geometry, fine. It's just a network, just a transformer. Give it to them, he's going to understand how to use it, which is great, I think. Besides that, VGGT is very good out of the box for many things. Good camera pose prediction, point map prediction, but without training specifically for this task, it's also good for multi-view stereo, monocular depth estimation, 2D matching, and also 2D tracking for non-rigid objects. Okay, you can use those features to get state-of-the-art 2D tracking too. So this just are indications that the model is scaling well, because when it starts to work well on this large variety of problems, even without being trained specifically for them, that's an indication you're doing something good with your model. Okay? Of course, there are limitations. So this scale up well, up to 300 images, after which you run out of memory in your GPU. And so if you want to reconstruct Rome in a day from, say, 100,000 images, then you're out of luck. In this case, you would still need to combine this with some optimization in post-processing. But if you're not targeting this sort of problems, then this is a very reasonable way of performing 3D reconstruction now. In fact, I'm going to try to give you a little demo of this because I like risks. And we'll see where this works. So this is a Hugging Face demo. You can try for yourself. And these are a bunch of images I collected this morning walking to the conference center, walking across the street here in Nashville. So I'm going to put them... if I can, okay, maybe I should select all of them. The hardest thing here is to select the images, you know. And then you can drag them here, and hopefully the interconnection is going to work. Let's see. Uploading. Internet, do your thing. There you go. See? You just need to speak to it. And the internet listens to you, apparently. Okay, then you press reconstruction. Yes. Okay, but I ran it before, so you would have seen this. Okay. So yes, voila, that's the result you get. Okay, so it works. Okay. So tell to my manager in Meta that we should buy a Hugging Face subscription, I guess, or something like that. Okay. All right, there you go. So let's carry on. All right, so that's come on. That was VGGT. I want now to switch gear a bit and talk about dynamic reconstruction, which was talked about in the previous talk. So I wanted to give you also my perspective on that. And what I want to introduce here is a 4D representation, which I think you can take, and maybe the next version of VGGT is going to use it. Perhaps, we'll see. But the point is that we want to propose a representation which is really good for representing not only 3D static things like point clouds do, but also 4D things as well. So the concept here is point maps, which is, again, popularized by Duster. The idea is to each pixel of an image, you associate a three-dimensional point. And this is good, especially when you do that for two images at the same time. And the key point here is that the second time you do it, for the second image, well, actually something changes, and that's the viewpoint. So what you want to do is to perform a reconstruction with these dimensional points per pixel in a way which is always referred to the viewpoint of the first camera. So these reconstructions are view invariant. Okay? This is really, really crucial. Without this view invariance, this is not useful, or at least not that useful. In fact, when you have this view invariance, then good things happen. So let me unpack this for you a little bit. So what happens here if you have two images, I1 and I2, we have two viewpoints, pi1 and pi2. Okay? And what we want to get are point maps. I'm going to denote one of them, which is called P2 here. P2 means that the 3 points here come from the pixels of the second image, okay? But the viewpoint, pi, comes from the first image instead. So you can see that there is a sort of crossing information between the two views, right? This is where things actually communicate. And once you do that, then you get useful properties, because you can use these point maps to get fused point clouds, but also correspondences. For instance, here, if you have 2 points on a cube, U1 and U2, and you want to know that they're the same, all you need to do is to compute the corresponding point maps. And because these are view invariant, then 3D points that you're going to get must be the same, right? So, but checking whether 3D points are the same or not, you know whether 2D pixels correspond or not. So these point maps are encoding also 2D correspondences. Okay? Do you spot the problem? Did you see the problem in this slide? I'm sure one person did, but it's too shy to say. So the problem is here. Right? So the problem is that this works for all the points in that scene except for the cylinder. And why? Because the cylinder is actually moving, it's not static. And so if you do this exercise again, and if you compute the point maps for the two pixels you have here, U1 and U2, then you get different 3D points. And it means that these do not coincide anymore. You don't realize that these are the same physical points because they move over time. Okay? So the dynamic point maps are going to fix this problem with invariance. So to fix the invariance, instead of doing 2 point maps per image, so per pair of images, what we're going to do is to have 4. Okay? And we're going to introduce the time variable. So let me unpack this again with the same notation as I used before. We have two images, I1 and I2. We have two viewpoints, pi1 and pi2. But we also have two times, because the time is changing. So we have T1 and T2. Now what we do is, from the pixels image 2, we extract corresponding 3D points. We do that with respect to the viewpoint of the first image, same as before, but the time can be either for image 1 or for image 2. Okay? And this is going to fix the problem. For example, if you want to recover the invariance to time, all you need to do is to put the same time variable in both point maps. And now, although the point and time are changing, you reconstruct everything against the same time frame, and you're going to restore the invariance, so you can identify corresponding pixels. But you can also do the other way around. So if you can fix your attention on one image, compute the same point map twice, but under different times, what are you going to get in this case? Well, you're going to get an estimate of the 4D flow, the 4D motion. And would argue that if you want to do 4D reconstruction, it's not enough to do a collection of 3D reconstruction of each frame. You really also want to reconstruct the 4D motion. You have the 4D flow. And this is what the representation encodes for you. It encodes both the geometry, the correspondences, as well as the 4D flow. The way we implement this in practice, this was not done in Meta, it was done at a much smaller scale in Oxford. So we take the master network, we add a couple of heads to it so we can get 4 instead of 2 point maps, and then we fine-tune the model on synthetic data. And if you compare this against popular representations now for dynamics, for example, Monster, this is dynamic point maps, and this is Monster. Monster has this problem that does not fix the invariance to time for the geometry, but ours do, okay? And in the previous talk, you have listened to the very interesting paper, Star Trek, which is very similar. It would be these 2 points cloud here, okay? Whereas we do 4. Can you get away with 2? Yes. If you get the other 2, you get a bit more information. But these two ideas are very, very, very close in practice, okay? And both of them are going to fix this problem that Monster has, okay? All right. And with that, you're going to get results which are similar to what was shown in previous talks. So for the reconstruction, works okay. But most importantly, what you get is a reconstruction of the 4D motion as well. So you see here motion segmentation, as well as some, it's very hard to see, but there are some thin lines here which are 4D tracks. And you can recover that from this dynamic point map representation. Okay? And if you do depth prediction evaluation, this performs pretty much like a monster. What this wins out is the computation of this 4D flow. Again, because this directly does it, as opposed to doing like in monster, in which case you need to combine monster with 2D optical flow like raft to recover the 4D motion as well. So it's just a more complete representation that really is, I think, the natural extension of point maps to the dynamic case. So I hope the future model is actually going to adopt, if not our weights, at least our representation. Okay? All right, great. So that was motion. And what about appearance? So at the end of the day, this is a talk on digital twins, and digital twins are not just geometry, they're also appearance. So here's a scene, and there are two objects which are fake. Can you spot the objects? I suppose yes, but tell me no, so I'm happy. Okay, so these two objects are fake, okay? But the idea here is we want to reconstruct objects in a way that is not just good for geometry, but is done in such a way that if you put the objects in a different lighting situation, then they blend well, and so they look like they belong to the scene. So this is what I'm going to spend the last 10 minutes of my talk discussing. So feed-forward digital twin creation. And this method is called Twinner. It's also a poster here at CVPR, so if you're interested, you can check out the poster later at the conference. So the idea here is we're going to start from multiple views. We're going to use 4, and then it's going to be a network that in a feed-forward manner gives us the geometry, okay? This is object-specific, object-centric. It's not a scene, it's just an object. But crucially, also it's going to give us the materials, so we use PBR materials for that, and an estimate of the illumination, okay? It's actually quite difficult to do. It's very, very reposed, but we still get kind of like reasonable results, actually, okay? And part of the reason is that in the images, you do see the background, so the network will use these cues to actually try to generate a illumination map, which is actually important. Now, colors are, of course, view-dependent. We know that because we know about the radiance fields. So what is a radiance field? A radiance field is this function here, L, that is associated every point in space P and every direction nu, a given color, right? So when you get your image, the RGB value you measure a given pixel will be essentially the radiance which is emitted by the nearest non-transparent point in three-dimensional space, which is going to emit light in that particular direction. So the radiance function looks something like this. Is a function of a direction, a point, and it gives you the amount of energy that the light is transferring in a given cone along a given direction with respect to the normal to the object, to your surface. Okay? So that's radiance. It's just a snapshot, though, of the illumination you get in a given scene. This is not enough, though, because what we need to do is to be able to compute how the radiance function changes if we change the illumination. Okay? This is what NERF would capture. That's not enough for our purposes. What we need is to estimate reflectance instead. So what is reflectance? Reflectance is a function that tells you if you have illumination that gets into this point from the scene, for example, from the environment, how much of that energy is reflected along a specific direction as a result of the material. Okay? It explains how light from the environment bounces off the material into all different directions in space. And this is what you actually see. What you actually see is the interaction between the material and the illumination that comes from the environment. Okay? There's a bit of notation here. It doesn't really matter too much, but what it matters is that we need to learn this function f, which is going to tell us at every given point in space how the lights will reflect when it comes from a given direction omega and is reflected in a given direction nu. So this is a function of several parameters, and in particular p, omega, and nu, the position in space, the incoming direction, and the outgoing direction. And once you know that, to compute your image, what you need to do is to integrate for all possible incoming directions what's going to be the reflected lights, and then you sum them up over all possible incoming direction, you're going to get what you're actually going to see in a given viewing direction. Okay? Now to do that, what we need to do is to model this function f, and to do it, we're going to use the GGX reflection distribution function, which is a function which is designed by computer graphics folks, is physically inspired, although not physically accurate, and it depends on a few parameters. This is a parametric function. In principle, at the RDF, it can be very, very complicated. Here, we reduce it to a function which depends on 5 parameters only. It's going to be the albedo, which is essentially the color, if you like, the texture. It's going to be the metalness, which say how metallic-like something is, and then there's going to be the roughness that tells you whether it's a rough material like rock or is a shiny material like a piece of glass. Okay? Now you may wonder, what's the relationship between these 5 parameters and this function here? here it is. Take a snapshot if you like, or look it up in a book. It doesn't really matter. The point here is that this is a closed form. So you can put this into PyTorch, and you can differentiate through, no problem. It's just a little bit nasty to look at the first time you look at it. Okay, so now we have our GGX function, how we're going to use it. And here's how. So first of all, we design an actor that given 4 images as input, will produce as output the occupancy, which is just like NERF, what captures the shape of the object. And then at each given point in space, we're going to have the albedo, RGB color of the texture, as well as the metalness and the roughness. Okay, we estimate all those things, so we get a good representation of what the object looks like from a physical perspective. I mean, at least for the materials. Okay? And all of these are volumetric functions that we estimate using a network. Now, one thing is, how are we going to represent these volumetric functions? And so here we introduce something which is a little bit new, which is called a tricolumn representation. So one thing you can do is you can take your network and output, say, well, a function f using an MLP. That would be NERF, for example. So at every given point in space x, y, z, the function f is going to give you one of these parameters. Could be RGB, could be albedo, could be roughness, or realistically a vector of all of them together. But to make this work well, we want to use a transformer, because why not? Transformers are what works the best. So we can have a bunch of tokens, and somehow we want to use these tokens to encode this three-dimensional volumetric function. It is a choice on how you do that. So one way would be to use a volumetric representation, a voxel grid. So here we break the space into voxels, and each voxel becomes a tokens. This is totally fine. It's very simple. It works well. Problem is that you have too many tokens. And if you have self-attention for these tokens, then this is going to blow up. So we don't like that because it's just too heavy when you look at it through the lens of a transformer. Another thing you can do is to use triplane representation, in which case you end up projecting information down to the 3 different planes. And now you have one token for each one of the squares in which you have broken down these planes. So instead of being cubic, it's quadratic in the number of, in the resolution of your voxel space. So being R cubed is R square, okay? This is much better, but the problem with this is that each point in space now depends on the projection of functions on 3 different planes. What does it mean is that each one of these values here really encodes the entire column of voxel values along this line, right? And that makes it a little bit confusing because this token now represents a whole lot of stuff, not just, it's not localized information. So this is not really great. So what we did here is to use what we call a tricolumn representation, which is what this slide should say. It shouldn't say triplane, but tricolumn. And that's a blunder. Yeah. Okay, sorry about that. But the point here is that we still operate as if it was a voxel grid, but then we group all the voxels that we get in each one of these columns, and we treat it as a single token in our transformer. Okay? That's how this works. Yes. Okay, right. So this is it. So now we have the advantage. This is somewhere in between a voxel grid and a tricolumn and a triplane. So we have a relatively small number of tokens, but each dimension in the representation is still very, very local. All right? And this gives us actually better representational power in our model. And here it is again. So voxel, triplane, and tricolumn. And we have some more that goes into with this model, which is a very fast and efficient implementation of this using kernelized, using CUDA-optimized versions of the kernels that actually needed to render this representation on the screen. And so with this, we get a very efficient way of using this tricolumn representation to represent this function and render them on screen. Okay, now, how do we train this model? First thing we do is to use synthetic data. That's great, it works very well. I suggest you use it if you can. So you take 4 input images, put your network here, you're going to get your RGB and material maps, and then you render them as images, literally, but you don't actually account for illumination. You render directly the channels, albedo and metalness and roughness. You get the same from your ground truths, you compare them as images, you minimize. And that's fine. You can definitely do that, but that requires to know the ground truth values for albedo and illumination and the materials, right? What happens if you do not? And for that, you can, for example, use zeroverse, which is a randomized data set of random shapes and in which we have augmented with random materials and random illumination, and that's fine. And that gives you already a very good model. But what if you want to use zero data instead? Well, this is a lot harder because you don't get this decomposition in the ground truth. You only get one view, right? And so how do you connect these 3 things here, the material, the shape, and the albedo, with the view you actually do see? Well, you're going to use rendering. You need to use the differentiable rendering. And again, we have fast kernels to do it. That's good. But this is not enough, because to go from here to there, you also need illumination, right? This is missing here. So what we do, because if you change illumination, actually, the appearance of your object will change accordingly. So in order to figure out the pixel value you're actually going to see in real life, you also need to estimate what would be the illumination. So to do this, then, let me skip over that. So what we do is we task our network with estimating also an environment map. Environment map is a way of encoding the illumination you see in the screen, in the scene. And once you get these ingredients into your PBR renderer, then you're actually able to render the pixels in the physically correct way. And with this, you're actually able to train the model also on real data. Okay, enough discussion. Let me show you some examples, and then we'll stop. So here are some examples you can get from this particular model. So it's 4 views. You get out the geometry, the roughness, the metalness, and the albedo, as well as an estimate of the environment. Of course, this is very, very rough, but this is actually super difficult to get. So this is actually already considered to be a good result. Will it blend? Kind of, I guess. So if you take this small object and you put it back into render views, where the illumination changes a lot, well, it looks pretty plausible, right? In terms of quantitative results, so these are methods that use iterative optimization, whereas our method is feed-forward. And so we get results which are not quite as good as the iterative methods in this case, but they're very encouraging. And this is a comparison with a method that we introduced last year, which was called Metal-LLM, which is in fact much worse than Twinner in terms of PSNR when you do reconstructive illumination-dependent views. And we're starting to be competitive with a method that would take much longer in terms of runtime. So this takes 10 seconds. This would take 10,000 seconds, say. Okay. So it's really good progress. And yes, if you do some ablations, you'll see that if you run using our shading loss on real data, then your PSNR grows actually quite a bit compared to only using not using real data, not using the static data either. And these are some example illumination that are recorded by the model. So this is the ground truth, this is what we get, and this is what 2 other competitors do get. And now it tends to be better because we have much stronger priors for the network we learn. And then, just to conclude, some final results for input views. The results we got last year with Metal-LLM, and the Twinner method we get, the results we get with the Twinner method this year, which is much better. Another example with the toaster, which is very metallic, obviously. And one more with the apple. So last year this was estimated to be too metallic. Now it gets much better, a much better appearance, which is no metallic. And here's one more example. Okay, that's it. So conclusions. What I showed today are 2 things. First, in fact, 3 things, I guess. One, it was feed-forward geometry, static as well as dynamic, the GGT as well as dynamic point maps. And this is where we're really making very, very good progress. I think now, at least for the static case, we're at the points where you can take your feed-forward model and go integrate it with a large language model and be happy with it, because you don't need optimization anymore. And then for feed-forward digital twinning, well, we're making very good progress, and I think this is a super hard but super interesting task. As you can see, we're not quite on par with iterative methods, but we're getting there step by step.